First, this is an intermediate level technical talk, so it would help a lot if you're familiar with generators, for example, in Python, and in general, the concepts of concurrency, threading, locks, stuff like that. But if not, it's still okay. I hope you can still follow this. So who here is, already have used async IO in their in Python? Yeah. For those who are not yet familiar with it, I hope this talk will get you started in your next projects because it's really exciting. And for those that are already familiar with it, I'm aiming that this talk will still give you something, because my focus here is not really about the asynchronous aspect per se or the event-driven aspect of async IO, because there are lots of resources already about that in the internet already, not just for Python but for other programming languages as well. So what I'm going to focus about is the multitasking aspect of using async IO and the new async await syntax. So first, let's start off with basic concept. So what's multitasking? So multitasking is execution of multiple sequences of instructions concurrently, not necessarily, not necessarily parallel or physically at the same time, but just concurrently. So similar to, for example, you might be working, coding, and you might be checking Slack at the same time, and you might be checking social media at the same time. So you're not really doing one thing physically at the same time, but you just context switch, you alt tab, things like that. And similarly in Python, especially in Python, where because of the global interpreter lock, you can usually you're only able to execute multiple threads concurrently and not really in parallel, even if you have multiple CPUs in your, or multiple cores in your machine. And I don't recommend that multitasking, by the way. So yeah, there are many layers of multitasking. Like there can be multiple machines coordinating with each other. But for now, we'll just focus on threads and processes. Actually, we'll just touch process just a short bit, but we're more focusing on threads or thread-like multitasking, where in the same process you'll have multiple sequences of instructions concurrently executing. So a process is a task in an operating system with their own independent resources, like file descriptors, memory, like exclusive access to their own memory, and other resources specific to that operating system, like window handles, things like that. And they're independent, they're isolated. But for thread are tasks within a process with shared resources. So threads in the same process can access the same memory. For processes, the operating system needs to provide mechanism for inter-process communication, and there are lots of different means for that. But yeah, for threads, you can just use the shared memory that you have. So yeah, here I have some code that will demonstrate preemptive multitasking. This is what native OS threads do. So when you're using the threading library of Python, then by the way, can you see it? If you want to, you can access it here, by the way, bit.ly/pycon19-asyncio. It's a GitHub repo, so you can check it out more, but I'll just zoom it more. Yeah, maybe that's better. So yeah, we're going to use threading to demonstrate the native use of native OS threads. So preemptive means that you have, when you're multitasking, for example, one thread is doing something, then it can be preemptively suspended, and other tasks will be executing in place of it. So the thread itself doesn't have control on its execution or its time slice of the CPU. So here we have a counter object. By the way, I'm using Python 3.7. the latest Python version, but I think you can use this up to Python 3.5, but I recommend Python 3.7 because it has lots of usability improvements, especially for the async IO library. 3.6 and 3.7 really introduce lots of usability improvements in that. And then for Jupyter, the Jupyter notebook I'm using is also the latest because it has explicit support for the new async await syntax. Older ones might not work here. So anyway, so I have a counter class that basically has a value. You can increment it or decrement it. And then you have a function called incrementer. What it does is just increments the counter n times m times. So every m number of times it will increment it, and then it will sleep for a while just to rest, and then do it n number of times. So the same with decrement, it will just do it decremented. So we have a single counter, and then we spawn a thread using the incrementer and decrementer for a number of times. This one doesn't matter, you can tweak it, but yeah, the important thing is that for each incrementer, you have a corresponding decrementer. So the same value, so 30 times 40,000, so you should have 3 times, multiply that, and that's the number of times it will be incremented for each thread, and the same for the decrementer. So all in all, the counter should be 0, right? Since you increment that number of times and you counteract it with the decrementer. And then let's see what will happen, what will be the value. So as you can see, it's not 0. So why is that? It's a classic race condition. So it's difficult to debug, a high-sense bug, as you may call it, because for example, in your local development machine, you have different parameters for that. And in production, where it already has lots of values, then that's when it will show. So for example, you can try tweaking the values above and see that lower values of m does not lead to race conditions. For example, we just changed the value from 40,000 to 4,000. And yeah, it's 0 as expected. Why did it happen? It's because the larger value just made it more, increased the probability of having that race condition. So where does it happen? Let's see. Self-death value plus equal 1. So you might think that this is just one line. So it might the thread might be preempted, for example, somewhere here or somewhere here, but it's just one line. So why is it not does not have the same value? Because this one, in terms of OS level, because OS or native threads, you should suspends threads on an instruction level or CPU instruction level, and not really on a Python Python line level. And even Python instruction level, it's not atomic. It's not just one instruction. If you can see, let's disassemble the instruction using the this module. You can see that the actual bytecode for the increment, it has lots of instructions. So it can be suspended or preempted anytime here. So for example, while an incrementer thread loads the attribute value, here, for example, it stores 1,000, and then it was suspended here, and then other threads do its thing. So some other thread incremented it or decremented it a bunch of other times, but it doesn't see it because it already loaded the value that was before. So let's say you have 2 threads, an incrementer and decrementer. The one running is, for example, thread 2, and so far they're in sync. They have the same value for value, but thread 2 was suspended somewhere here, so its value is for value is still 1,000. Oops, this should be 1,000. Yeah. So, and then thread 1 is now running. and then it increments 1001, 1002, but thread 2 still has 1000 here because it was suspended here, somewhere here, so its value was what it was before. So by the time it resumes its execution, it decrements it and stores the value 999. So they're now not in sync with each other. So that's a race condition. Okay, now we're going to move on to using async IO and coroutines. So here, very similar, same definition. But now your incrementer is a coroutine function defined by having an async keyword in the function definition. And then instead of using time.sleep, you will await an async IO.sleep coroutine. This is also a coroutine, or an awaitable at least. And then similar for decrementer. So they have very corresponding definitions. And then, yeah, similar. And then you just await on all the tasks. Here, as noted here, you can only do this on the top level in Jupyter Notebook. So normally, you have to do something like this to run it, to run the initial coroutine that you're going to run. But here in Jupyter Notebook, it has a convenient way of just spawning your initial coroutine. So let's see. Let's wait for the result, and it's 0. Why is that? Because here there's only one thread actually executing, as in one thread, and the coroutines are just async IO just coordinates them. And the key thing here is, since there's only one thread and it's not native, it's not preemptive, the tasks themselves or the coroutines themselves have control on when they can be when they can be switched from being executed to yield, or as named here, it's cooperative. So they cooperate with each other explicitly. So this is for example, for both incrementer and decrementer, this is the only time they can other coroutines can execute. So when they await, then that's the only time. So for all the execution here, the increment, it's the coroutine is assured that it's the only one executing. So the case with the race condition won't happen because it's this one will, you won't have somewhere in here that will make it switch to other coroutines or other tasks. So as you can see, we can already see some value in using async IO and coroutines. So you can think of preemptive multitasking as the OS being a sort of a supervisor orchestrating the tasks. So for example, you have a bunch of workers, and then they do their tasks, and then you command who can do each. You only have one place where a task can be done, and then you command it like, the OS will, or the supervisor will assign one person, for example, to do this task, and then that supervisor will be the one that can, you stop it now, and some other will do it. So but cooperative multitasking is you don't have a supervisor. It's the different the people themselves talk to each other, or coordinate with each other, or cooperate with each other, and then they will yield explicitly. They will explicitly say, it's your turn, or it can be your turn at least. So as you can see, it's like we're all consenting adults here. That's the principle. But as you can see, there can also be problems with that, which we'll explore later. So usage, classic hello world example. So here you have a coroutine function that's printing hello, and then it will just sleep for 3 seconds and then print world. So very straightforward. So you define a coroutine function by having the async keyword, and then you print, and then you await This one provides an opportunity for other coroutines to take over. And then this one signifies that I will resume, or this coroutine will resume in 3 seconds. So, or it sleeps in 3 seconds. So, yeah, and then after that word. It doesn't mean that this just means that this can resume in 3 seconds or more, not 3 seconds exactly, because there can be no assurances on that. You can pretty much expect that it's, if not exactly 3 seconds, it's a bit more than 3 seconds where this will resume, because this is not real time, so there are no real time guarantees. Again, you can only do the above in Jupyter Notebook. Normally, in IPython, you can also do this. But normally, like for example, if you're in a top-level module, you can't do this, because you can only use await in a coroutine function. Yeah. So here, just some definition. So coro_fn is the coroutine function, while the one created by it is a coroutine. So a coroutine, as you can see when we execute this, this is function, and this is a coroutine. And as you can see, there's no printed hello, because yeah, it's just a coroutine yet. It's not yet scheduled. It's not yet executed in any way. So similar to threads, when you create a thread, it's just an object representing a thread, but it hasn't really started yet. And in terms of implementation, it's pretty much like generators. Main difference is that generators are iterables, but coroutines are not. But they have similar methods, like you can send. If you send it, you'll have hello. So that's when it will execute, and then it's already finished, it will throw stop iteration. Just a brief history. So async IO was actually introduced as the Tulip project. Guido himself contributed a lot to it, and it was introduced on a provisional basis on 3.4, and it was stabilized in 3.5. And the new async await syntax was just introduced in 3.5. So you might wonder, what does async IO use when there's no async await yet, or there are no coroutines yet? And the answer is generators. And you can still use that, generators, actual generators that has yield a keyword, the normal generator one. So you can think of await as yield, and yeah. You can still use generators in async IO, but it's deprecated now. It will be removed in a couple of major versions or something. Yeah. And await. So here await, it's awaiting. When you do await, it's not limited to coroutines only, because there's the general concept of awaitables. So a coroutine is an awaitable, but there are many more kinds of awaitables, and you can define your own awaitable. So that's the general style in Python. Like you can have lists, dictionaries, and generators, and they are generally iterables, and you can define your own iterables. So similar to that, you can. There's a general concept of awaitable. Basically, you just have to execute implement the dunder await method that has that's well defined. It has a protocol. So here, let's do the count. So it will just count from 0 to 9, and that's it. Again, you can only use this in Jupyter Notebook. Normally, there's setup required if you want to use it in normal Python usage. So yeah, so far okay. I'm just going to introduce to you some other awaitables that's defined by the async IO library. By the way, async IO library is not the only library that you can use with coroutines. So there are also other third-party libraries. Async IO is the one Matter included, but there are third-party libraries that have different style in terms of usage of coroutines. There's Curio and Trio, and maybe some other libraries. So yeah, you can use coroutines without using async IO, but here we're using them both. So task is async IO specific, so it is it's like similar to threads. It uses coroutines, and the advantage of that, it has a bunch of convenient ways to manipulate task. For example, you can cancel it. Let's see. As you can see, you can await a task. It's not a coroutine, but it's an awaitable. And it has an argument of count. A coroutine, not a function. You can't do this. For example, this will not work because count is a coroutine function. What you need is the actual coroutine. So here it will count, but there's a cancellation 3 seconds later. This call later is 3 seconds later, you cancel the task. So after 3 seconds, it's canceled. So what's good about this is that the result of the task you will get here, similar to coroutine, but aside from that, the exceptions as well. So it's not only the results, but also the exceptions that will that can be returned in an await. So here, yeah, you cancel it after 3 seconds, and yeah, later we'll detail more about cancellation and stuff like that. But yeah, task is the recommended way of creating background, sort of like threads. And then you have a future object. So future object is like a container where you can await on it, and then others can put result or exceptions to it. So for example, you have hello and world. You pass them both futures. They will just pass objects to each other. So you can use the gather function in async IO, and yeah, when you call them world hello with future, so they will be executed almost at the same time, or scheduled almost at the same time, and yeah, you have it here. So future, you created a future, and then you set the result, and then when the world waits for the result of the future, then once it's set, you have it. So it's one of the data structures you can use to communicate between different coroutines. And then event loop is what actually runs in the background, that actually executes it. So yeah. And then yeah, what are the advantages of, yeah, the details of this is is out of the scope of this talk, but yeah, I just talk about advantages. Explicit is better than implicit. This is one of the maxims in Python. Here, you know the places where a coroutine can possibly be suspended. Like for example, as mentioned earlier, in await, that's where you know that you can be suspended. So between this, you know that there's no place, you won't be preempted, or the coroutine won't be preempted. So, and then there's sensitivity. So yeah, let's try executing it. So it's sensitive. So to be able to use a coroutine, you have to be a coroutine yourself. Yeah, but you can schedule it differently. Like you can schedule it from a different thread or from something that doesn't use async IO or not in a coroutine itself. But in general, like because you can only await if you're a coroutine. So when you use coroutine normally or in normal usage, you have to use await. So yeah, there's a chain of coroutines in that. It's lightweight as well. Since it doesn't use a full thread, in native OS threads are relatively heavy. Like, depends on the operating system, but it's relatively heavy. So for example, you can have 10,000 or yeah, 500,000, 100,000 coroutines without a problem. You're just restricted by the amount of memory you have. But yeah, you'll see here that the overhead is not that much. You waited, the overall, it just executed in 8 seconds. But if you use threading, for example, this is just an idle, just sleeps for 5 seconds and doesn't do anything. We're just checking here the actual overhead of creating a thread. And it's a runtime error because there's no more resources enough to start a new thread. So you can see one advantage already. And you have better control. So, for example, as seen earlier, you can cancel a thread or a coroutine. Thread, it's dangerous to forcibly kill a thread because yeah, it can pretty much die anywhere, so it's not recommended to do it. Even though some operating systems provide a way for you to do it, it's not recommended because you can be in the middle of resource deallocation or destruction, and then or some other thing, and then yeah, you're in a bad state. But here, the key thing here is that it can only be canceled during an await. So for example, if you're doing this, you won't be canceled somewhere here in between. Even if you do a bunch of stuff here, it won't be canceled there. You can only be canceled while you're yielding. And Async.io is the one coordinating that. So yeah, that's one. And then timeout. For example, you want to wait for a task, and then you want to have a limit on how much you'll wait. So similar here. So there's a wait for. You wait for a task for 3 seconds. This task is not limited to tasks. It can be a coroutine or a future or any awaitable. But yeah, Async.io provides that convenience for you. And then it will show a timeout error if it doesn't return for that much. And again, similarly, yeah, if ever this is canceled or something like that, this won't be canceled in between. Actually, I'm not sure this is actually canceled, but because this is just waiting and not a cancellation. But yeah. So, okay, I'm going to introduce to you. Wait, I thought I have 1 hour, or is that? Yeah. Okay. Okay, I'm going to introduce to you a problem. A restaurant simulator. So, in this restaurant simulator, there are lots of actors involved, and they coordinate with each other. And yeah, you can use it, for example, for trying to simulate like how many tables you should have, or how many waiters or customers, the customer rate. So this is just a simple one. There's just a lot of code, and I'm not going to go through it one by one because we might have time for that. But so yeah, I'll just execute it first. So I'm going to seed the randomizer so that we can have consistent results. So yeah, for example, it just prints customer 1 enters, customer 1 is seated at table 0, and then the minutes here is just basically seconds, but we just time it as minutes. But it's in real time, it's just in seconds. So yeah, it helps if you're familiar with the locking primitives and other data structures for coordinating concurrent execution. So, for example, when you enter, you create a future. There's a corresponding future also for threads, which is under concurrent.futures. So it's actually earlier than the async.io.future. This concept is earlier, the concurrent one. and you have a queue, and you just put an event. There's an event that enters, and then and then you wait for the result of that. So this one just indicates if you're ready to be seated, something like that. And there are a bunch of other functions that can be done. So you have different kinds of. You have the customer, you have the cook, and you have the waiter. So there are lots of locking involved. Like for example, when you want to check if there's an occupied table, then you have to lock it first so that other threads won't in between get the table, and you don't know, you might not notice that the earlier table is already free or something like that. So you have to lock it for the duration of checking all the tables, because you can have multiple tables, and in between that iteration and enumeration, you get to have different inconsistent view of that. So yeah, the time that sleep is just basically a simulation of how much time it will take to do that. So 1 is for 1 minute. So let's just stop it for now. So there's a bunch of output already. And I'm just going to restart the kernel so that all the threads that's probably running will be stopped as well. So let's try to convert that to hello, can you hear me? Oops. Sorry. Let's just try to convert that to using async IO. So we're going to remove this, we're just going to have import async IO. So one of the things that you will not need anymore are locks. I mean, there's still a concept of lock, or you can simulate locks in async IO. There's async IO.lock, but most of the time you don't need to use it because because you have control on your execution. So you just don't in cases you need a lock, you just make it so that you don't yield, so that you're sure that there's no intervening thread that will interfere with you. So here, put no wait. So this is interesting because queue has 2 signatures for putting, but since our queue doesn't have any limit, then you can pretty much be assured that you don't have to wait. But if you use the put here, you can do that, but yeah, you don't need to. So here you define it async, and then you can await it. Yeah, something like that. We have an equivalent here, get running loop. So order food, you have an equivalent, and then here you also have put no wait. This one you don't need to define as async because you don't await anywhere. So if you want to wait for food, then here you have to await. So as you can see, those primitives like the event one, when you want to wait for it, you have to call await, because this will return a coroutine or an awaitable. So when you leave, similar, you don't need to do anything. You don't need to await on anything. A waiter is, when you have an event. Here, you don't need a lock because, for example, when checking the tables, you can just, there's no await. So you know that you're in control during this time, during this block of time, during this block of execution. And then async IO, that's sleep. And then, yeah, this one still need the completion to notify the cooks that there are already dishes. Async IO, that's sleep. And then here, it's ready, async IO, that's sleep. So okay. Here, yeah, you have 2 locks here, and you don't need both. You don't need both of them. Seat awaiting call. Because again, you don't really have anything here that's awaiting, so you know you're safe. Again, we're going to define this as a coroutine, and then wait for this one. We have to await time that sleep, async IO sleep, and then put no wait, and then async similar await here. Order doesn't need awaiting. This one needs one. Async IO, that's sleep, await. And I think we pretty much converted it. So we just need to make it similar. So you have async create task. Similar to here. And lastly, you have customers. And then you have await.
I think you missed a parenthesis there. There are 2 parentheses on the last 2 lines.
Last 2 lines.
Second to the last line, sorry.
Second to the
There's
last.
2 parentheses, so it should be only 1 at the end. Oh, that's actually correct, sorry.
Yeah, yeah. Okay.
I missed it.
Yeah, but thanks though. Okay, we're just going to run it as well. Hopefully it works, but if not, I have a backup. Oops. I think I missed something. Oh wait. Anyway, I have it here. I probably missed something, but yeah. I think the most important thing that we were able to remove is the locks, because now you have more control. You don't need to be worried that something will intervene. So yeah, I'm not sure why it's not executing. Start. It's going to restart it. Yeah, here. So yeah, as you can see, since we seeded the randomizer, the results should be similar, the same as the threaded equivalent. And yeah, the advantage of this is that since it's lightweight, you can actually pretty much speed this up and even add, for example, more rates without worrying about the thread overhead. So yeah. Okay, let's go with the gotchas. So some things you need to take care of. For example, since this is a cooperative multitasking and with great power comes great responsibility, you have to be actually cooperative. And it's easy to miss being uncooperative. For example, you're calculating you're using the CPU for a lot of time. You calculate like, you iterate for 5 million times and you do that. Let's see there's, so as you can see, the counter just sleeps for a half a second, but yeah, it hoarded the CPU, and yeah, it waited for a lot of time. So there's two main solutions to that. You can yield every now and then. Like for example, for every 10,000 loops, you can just yield explicitly. And as you can see, it didn't affect the other too much. It can still affect it, but the issue with this is there's an abstraction leak. There's a leak of abstraction on how you do things. And for example, you have to tweak the value. Are you going to wait every 1,000 times or 100,000 times and things like that? So that's a disadvantage. But at least it's still cooperative. One advantage is you have one that's spawned in a different thread using run in executor. Yeah, as you can see, it goes through well. But the problem with this is that the one that you're executing, like the compute here, you should be careful because now the invariant is broken. There are now two threads that can run at the same time, so you should limit these computations and treat it as a black box outside of your system. Like for example here, it's good because you just limit it to actually just computing the value of n. And yeah, it's okay. And then one other common thing is not awaiting a coroutine. So for example, you just call the coroutine, and just calling it, it's not a function. You have to be able to schedule it, so it needs to be awaited. But there's since it's very common, there's a warning to that. If a coroutine is, the issue is when you assign it to something, you won't see it because it's assigned, so it's not yet deallocated. It's only during the allocation that you'll see it. So basically when you delete the coroutine and it's not assigned anymore, so you can see the exception. And then there's the warning, I mean. Then there are also swallowed exceptions. So as you can see here, the task is yeah, calling do something, but it doesn't actually exist. So you didn't see it. Yeah, there's no, the exception was swallowed. You can only have a warning on it when the task itself is already going to be garbage collected or something. And yeah, for example, when you assign runner to none, because it will detect that task, the exception was never retrieved, so it will be emitted as an exception as well, and then you can see it here. You can enable debug mode to make it easy to detect stuff like that. Okay, so yeah, for example, when you await, when we do the first thing, it will warn you if something takes a lot longer and probably hoards the event loop. So you can see here, there's a warning on that. And then this one, when debug is enabled as well, you can see where exactly it is. And then this one, you can see the more detailed traceback. So yeah, that's it. I hope you learned a lot. And we're now Q&A.
Yes, any questions? Raise your hand. Just give me a round of applause. Any questions? One by one. I can't handle async here.
Use async, you don't need the threading module. Is that correct?
Yes, that's right.
So meaning, is there any place that the threading module is useful? Because it's, as far as I know, it's in the standard library.
Yeah, you can still use it. Like for example, in this example, where is it? In this one, we're actually executing a different, we don't use threading directly, but you're executing a CPU intensive calculation in a different thread. So this one has actually a different thread from this one. And you can use it on stuff, on external stuff usually. Stuff that, for example, for third party, for communicating with other for communication with legacy code that you don't have a control. And for stuff like this, it's a heavy calculation. For example, you're calling into C code or other native code, and there's no really integration with async IO. You just have to be careful with that, and you just have to try to limit those and explicitly mark those so that it will not pollute your system or your application code that just uses async IO.
Cool. Other questions? Raise your hand, please. Okay, I see.
Hi, I'm Pepe. So, I guess additional comment to what he asked when it comes to threading. So, async IO is pretty good when it comes to it doesn't do as well if some of the functionality that you're using is blocking. So let's say you're trying to get a API request. So that blocks basically it blocks the flow of the execution. So even if you use async IO, it wouldn't be able to multitask. So if you're using modules that don't support the async IO, you might be better off using threads. But for common tasks like requests, there are equivalent async IO friendly modules for it.
Yeah, that's a good point. So not many libraries don't actually integrate with async IO yet. So if you're going to use like blocking tasks like network requests, it has to have explicit integration with async IO in order for you to be able to properly use it.
Other questions? I'll take 2 more at the most. Okay, this one over here.
Hi,
Hello.
I'm Mitch. So first of all, that's a great talk, and I've been using like async await, but not in Python, like in JavaScript. And it seems like very similar. I've been wondering because like in JavaScript, of course, it's like with rendering UI and that sort of thing, and a lot of that is asynchronous. So that's the application. But for Python, what do you find yourself using async IO for?
For example, in our company, Insync, since we're a syncing application, we have lots of moving parts. We have lots of different, for example, tasks that do different things. And the thing that really makes it good for me is that you have better control of the task, like better coordination. You don't need to, for example, use locking because you know that everything is explicit. And that control really helps in reducing the number of bugs, like the race conditions that you have. And for example, in the web server world, for example, IO HTTP, an HTTP server that uses async IO is one of the has good benchmarks in terms of performance. So you can also use it for that. Like before, there's a Greenlet and G event. That's what you use for GUnicorn and stuff like that for web servers. And now you can use async IO. And the advantage of async IO over Greenlet and G event is that it's explicit. You know exactly where it can be yielded because of the transitivity of being on coroutine or an async function. So yeah, you can also do it. But what I like the most is really about the logic and the control that you can get when you have multiple tasks, multiple coroutines executing at the same time. There's better, it's more clear, it's more, there's less thing to worry about because preemptiveness really brings a lot of implicitness in that sense.